Alright, so here we are with Chapter 3, Section 1. We're going to use exponential functions to solve problems. Sounds like a plan. So, as we work in exponential functions, we're just going to want to just remember some of our rules for laws of exponents. So, if you are multiplying two things that have the same base, as we are in this multiplication rule, you would add the exponent. So a lot of times I think of kind of groups of things. So when we think of more positive operations, we think of adding and multiplying because we're growing, versus negative operations, which are subtracting or dividing. Alright, and so as we look at kind of grouping these two pieces together, notice that if you're multiplying, you also do the positive of adding, or if you're dividing, you end up doing the negative of subtracting. Another thing is powers as well, so powers end up being in that positive growth aspect as well, and so if you see that you have a power of a power, you end up multiplying. So each of those is like in that positive category. The next piece here, this is more of a distribution idea. So if you have two different bases, notice all of these were A's, and this now has a B in it. So if you have two different bases, you can go ahead and bring those each individual base to that power. Same thing for if you have two bases, again, you're distributing here as well. So here we are with two different bases. Then we also have that reiteration of anything to the 0 power is 1. So anything to the 0 power is 1. You can also imagine that there might be something very large inside of a parenthesis raised to the 0, and so that's still going to be just 1. And then we have this idea of a negative exponent. So this was introduced in Algebra 2, so just so that we remember, negative exponents really mean that you're bringing it down to the denominator and making it a positive exponent, but with that same base. Another piece that was introduced in Algebra 2 as well is that if you have a fraction as your exponent, that fraction denominator is actually the value of its radical. So a y numbered radical brought to that numerator or x power. Alright, so when do we use exponential functions? So anytime that we're talking about interest rates, okay, so you're getting a loan or whatever it happens to be, population changes, we like to talk about especially bunnies growing exponentially, growth and decay, so there's also decay rates. A lot of times, especially from the word decay, you think of elements decaying, having less carbon in them or whatever it happens to be. Or decaying in radiation, but we also have things that decay, like, for instance, the value of your car, or whatever it happens to be. And then we also have mortgages. So all of these use exponential functions to kind of be able to pay off your debt, or whatever it happens to be. So in exponential functions, we have the format of a times b to the x. We tend to use b a lot for this thing that's being raised to a power because of the word base. So b is your base. And then a, as of any other function that we've had, a is that number out front that makes it flip over an axis or perhaps stretch or compress it. So in officially exponential functions, a is your initial value, so it's that starting value. And b ends up being your rate, your growth rate as a decimal. So if they say that your rate of your loan is 3.5%, 3.5% actually equals 0.035 when it comes to the b value that would be indicated. We'll also note that if that b value is between 0 and 1, which this one is, we're talking about a decay, versus if it's a growth, it's over b. So that is exponential functions. We don't really have a group because, hey, we're not in class. So we need to consider this basic exponential function. So if b actually equals 1, we're taking 1 and raising it to a number. Well, 1 times 1 times 1, no matter how many times you do it, is going to be 1 always. So if b is 1, you're just doing a times 1. So the answer is just going to be a, meaning it will never grow or decay. What happens if a is greater than 0? So if a is greater than 0, that means that your initial value is a positive. So if a is greater than 0, you're going to start above the axis or in the positive values. And depending on what the x is from that case, you could be going down or up, so kind of just depends. This next one says that x is less than 0, so x is negative, and so that's going to be a decay. Sorry, that's not what I meant. If x is negative, we go back to that idea that you've made that negative, and so you've technically made that b value negative, not this b, but the b value in how you arrange equations and make them wider or flip them on axis. And so if x is less than 0, we're actually going to end up flipping it over the y-axis. Then what happens if b is less than 0? So if this base right here is less than 0, and that actually comes from the previous page here. If b is less than 0, it actually is not possible. Because what happens is you are saying that your rate is negative, which doesn't actually mean that it's decaying. It means that you're actually going to take a negative number to a power, and so it's going to switch between negatives and positives, and so it's going to make this kind of like graph that just goes like that all the time. So it's actually not possible, especially when we're talking about continuous growth or anything like that. And then the last option here, what happens if b is between 0 and 1, and so that is your decay. Versus this other one. Again, people think in number 4 that that's decay, but that's actually just not possible. Taking a look at what I was trying to explain earlier, what happens is we have that general transformation equation of the a value up front, the b value by the x, and then your h and your k. And we did do exploration with that last year, so the idea is that with this specific exponential equation, if you have this number up here, which I was just describing in this problem right here, if x is less than 0 or negative, that means that you have something flipping over the x-axis. Or sorry, y-axis, yeah. So I guess we can talk about each of these. So your a value in this case is going to talk about how it might flip over the x-axis if we're talking about a negative a. And if your a ends up being positive, it's going to stretch the graph vertically. And if a is negative, it will compress it vertically. Then we have our b values, and so our b value, again, if it's negative, it's going to flip it over the y-axis, so left to right. And then, as we talked about when we were learning this, if b is positive. Sorry, I'm getting my positive and negatives. Actually, positive and negatives with fractions and whole numbers mixed up. So what I meant to say is that if a is greater than 1, it will stretch it vertically, and if a is between 0 and 1 as a fraction, it will compress it vertically. So the same thing goes for the b, which we did go over in the previous slide, but if b is greater than 1, it actually flips what we're talking about, and so it's going to greater than 1, so it's going to compress horizontally. And if b is between 0 and 1, it's going to stretch it. So again, it does what you think backwards. Then we also have our h and our k value. So your h value is going to be the opposite. And so if h is positive, it moves something to the left, even though positive numbers feel like they move to the right. And then if h is negative, it moves it to the right. The idea is that we're examining this entire statement. So we're actually talking about if negative h is positive, which is just the opposites, but pretty much we're just talking about left and right is opposites. And then over here for k, that one is exactly as it is, so up for positives and down for negatives. Alright, so then we have our exponential growth or decay in the way that your a formula sheet might present it to you. You do sometimes on your MCAs or different testing, you will get formula sheets, so just taking the time to look at what they're coming up with for what we actually have seen before. So for instance, they're calling this a P0. A lot of times they use P because they're talking about population, and then that 0 is just kind of talking about the time being 0. So P is your population in this exponential growth and decay. 1 plus R is your growth or decay factor, and that's why we don't have any negatives in there, because you're either adding that rate to it. So if you're talking about that mortgage rate that I was talking about, it was going to be 1.00035, 3.5%. Versus if the value of a car or something is decreasing, you would do 1 minus 0.35. And so that is going to make it a decimal value, but not necessarily a negative. So again, no negatives for our B value, and so that's why we have 1 plus R here. And then again, R is your decay rate as a decimal. And then time is your T, and so depending on if they're talking about years or months, it'll just apply to each piece within that setup, and so you just want to make sure that the entire setup has its own years or months, and hopefully they're not changing between them. So in this one, they want you to find the initial value, the growth factor, and the growth rate of the functions. So the initial value, or P of 0, I guess we'll call it, is 3. So whatever this item happens to be, there's 3 to begin with. And then we have our growth factor. And so again, looking up here, our growth factor is 1 plus something, or in this case, what did they say it was? 1 plus R. So it's going to be 1.2. And then notice that since it's 1 plus R, if we want to find R, we would subtract 1 and get an R of 0.2. And so that's our rate, but of course we don't usually say it as a decimal when we think of it in terms of what things are possible, so a lot of times we'll convert it to a percent just to kind of get the same message out. Alright, and then the next one we do the same idea, only now they're saying it's starting with 2,500, whatever of the item it is. 1 plus R is going to be 0.89. And so in order to get the R by itself, we subtract a 1, and we realize that our rate is negative, whoops, where's my pen? Negative 0.11. And so in order to take into account that negative, that's why we say the word decay at 11%, or a rate of 0.11. So again, that decay or that negative sign is taken up with the word decay, so that we don't have to talk about the negatives, especially when we're trying to get towards that B value. Alright, so the next thing that we're going to look at is our value of E, okay, and so the value of E comes into play because we are looking at what we're calling natural logs. Basically, the idea is that there are opposite operations of things. So we have, for instance, multiplication and division are opposites. We have adding and subtracting that are opposites. We have squaring and rooting that are opposites. But then we also have things called powers and then logs. So if you are bringing something to a power, its opposite is actually doing a logarithm. And so I'll just write log. And I know that we did logarithms in Algebra 2. So again, this is just your opposite. And remember that natural log is the same as log base 10. We just use it if we ever have an e in the problem, because we are using things like finances to get our instantaneous, instantaneous rate of growth. So with that, we will also be introduced to something called the logistics function. I like to call it the rumor function, because the idea is that let's say that a rumor is started. There are only so many people in the school or the world or that have any reference to what's going on. And so if we think of it like that, this is kind of the number of people in the world, okay? And then the rumor that could be spread. So it starts with, one person tells it to another person, tells it. And what happens is in the middle of what's happening, exponentially it'll grow. But there's also this cap at the top, because you can't just keep telling people because they already know. And so the rumor function kind of has this limit to it. So as much as it's an exponential growth, it actually tapers off because it can only grow so far. Kind of like population, even though we're not seeing it technically, something's got to give because there's only so much space, right? There's only so much space or people to be telling this to, and so you have to have that cap. So this function is one that's bounded above and below because it actually has horizontal asymptotes at that base where it would start, and then at that numerator, or at that top. All right, so here we are with our logistics function, and again, it's given by this equation here. The logistics function needs a limit, so we did just talk about that. I gave some examples, but here they have the height a plant or a human can grow, okay, because there's only so high that someone can grow. I mean, I guess someone could grow forever for their whole life, but it's not happening. The number of fish in an aquarium, for instance, because again, there's only so many that can survive per square inch, and so you kind of have to take care of that. The spread of a rumor, as I mentioned, the growth of a city, because if the city gets overpopulated, there's only, again, so many physical spaces for people to be, and so, and of course laws that keep numbers of people per unit, and whatever it happens to be. So what's going to happen in the logistics function is that you're going to be presented with situations where they talk about the initial growth. And so the idea is that this is your exponential piece right here. And so when they talk about the initial number of people that heard the rumor or whatever it is, you're going to end up inserting this growth of, where is it? Of this type of equation. So you're going to end up having your exponential function within here, like ab to the x for your starting population and your rate, and then to that x value. So again, we will be going over this in the assignment, so here's your assignment that you will be doing next.